welcome the next speaker, Dimitrios Valsamaras. Dimitrios is a senior security researcher with a wide range of expertise, from mobile, web, and network pen testing to reverse engineering. Today, he will show us how third-party applications, without requiring any permission, can dispatch malicious content to other applications on the Android system. So, Dimitrios, the stage is yours.
Thank you. So hi, everyone. Thank you for joining, and thank you for having me here. I didn't know that I was going to be introduced, so I prepared a short slide about me. So as I said, my name is Dimitrios. I'm from Greece. I started my career as a network security engineer for about 10 years. Then I moved into developing for almost 5 years. And the last 6 years, I focused mainly on mobile security, while before I joined Microsoft's threat intelligence team as a senior security researcher, I was leading another team which was conducting malware reviews for the Google Play Store. Besides that, I'm a father of two, a boy and a girl, and in my free time, I try at least to write and play music. All right, so before we start, do we have any Android developers here? Only one? Any mobile security guys? Android specific? Okay, not that many. It's going to be hard. So, all right, so apparently many of you have some idea about class loaders, parcellables, serializables, and these kind of topics. So apparently also it's not all of you that have this idea. So I'm going to start with some basic things about class loaders, parcellables, serializables, just to give you a some base regarding that. And then we're going to go through some known issues, vulnerabilities that might occur when we are handling these kind of objects in a more secure manner. Then we're going to talk about custom classes. And what I mean by that, we're going to talk about classes that are declared in other apps. We can find them in some kind of public library, some kind of public directory. We can't import them in our project. And then we're going to see how we can create instances of these classes and how we can actually exploit the specific fact. So we're going to go through some specific vulnerability showcases to see how we can exploit such a thing. And finally, we're going to wrap up with conclusions and takeaways. So class loaders are an essential part of the Java virtual machine, responsible for loading binary representations of classes, interfaces. And when these are found, the JVM will load them, will construct first the class, the interface, and load it to the application's memory. They are usually implementations of the abstract ClassLoader class, reflecting, let's say, various loading policies, and they are organized according to an hierarchical model, according to which, on top of this model, we have the bootstrap or primordial ClassLoader, who is responsible for loading, as we say, the Java core libraries. And we also have user-defined ones, like the application or the extension ClassLoader, who are responsible for loading secondary classes for extension or application directories, as the name implies. When it comes to loading a class, class loaders follow a delegation model, according to which the lower level ones refer to their parents to find the class, in case they themselves were not able to locate the specific class. So this process will end up in either successfully loading a class or to a class not found exception in case no one of the nodes was able to locate it. Now, when moving towards Android operating system, so Android adopted the Dalvik VM as a move to address some of the limitations of the Java virtual machine. And since its initial, let's say, adoption, it went through a lot of improvements until it was finally replaced by the Android runtime in Android 5, fully in Android 5. Despite though this transition, Android runtime maintains compatibility with the Dalvik bytecode, and actually the whole process of Android application development and deployment didn't change much, I would say, through the last years. So Java, besides Kotlin, remains a mainstay when it comes to programming languages, and when it comes to running code, we have Dalvik bytecode, which is contained in Dalvik executable files, and is not compatible with the Java VM bytecode. In fact, in order to create a DEX file, we have to use the D8 compiler and pass the DS in order to integrate a class file to a DEX file, which finally can be used by an APK. Now, when it comes to the class loaders in the Android operating system, it was to mention the boot class loader, who is responsible for loading, once again, Java core libraries. And we have the default class loader for every app, which is the PathClassLoader. All right, so some other basic stuff about serialization in Java, which is something like, I mean, it's a trivial topic. So serialization, of course, is the process of converting an object into a byte stream, which facilitates the process of transmission of this object across different VMs. Either those VMs are within the same machine or distributed across a network. Now, for this process to be successful, apparently, the receiving end must be aware of the structure of the class of the receiving object, which means that this class should belong to the path of the receiving end's class loader. Now, moving to Android again. So in Android, moving objects between components like activities, broadcast receiver services is essential for inter-process and inter-process communication. So the adoption of a class, let's say, which was especially designed for this reason, for IPC, was unavoidable. So besides serializables, Android operating system uses parcellables for classes that can be read from and written to a parcel. So this class must implement the parcellable interface and must provide also a couple of special, let's say, methods that can be used to create a parcel out of an incoming one. Right, like the one create from parcel here method. Now, in order to create such a parcel and send it to another app, we have to obtain one. We can't construct one. We can't use the default constructor of the parcel class because this is intentionally remain private. So we have to obtain one using the obtain method, which dives into a pool of parcels. In order to obtain one, give it to the caller app, and when this parcel is no longer needed, it can be recycled and sent back to the pool. All right, so deserializations, you probably understand, can introduce vulnerabilities when the serialization source can be controlled by an attacker. And actually, MITRE has assigned more than 690 CVEs, if I'm not mistaken, for deserialization issues over the past 2 decades. For prominent object-oriented languages like Java, .NET, Python, and so on. Now, Android's though minimum reliance on Java, let's say, vulnerable libraries, has raised the bar when it comes to crafting deserialization gadgets. But not to be fooled by this fact, Android operating system is not immune to this kind of attacks. And here are some notable CVEs. So the first one in 2014 by Jan Horn, who proved that the object input stream didn't check if the incoming object did belong to a serializable class. This gave him, let's say, the opportunity to create objects of any class and send it to another app, to a privileged one in the specific case. Now, many of you might think, all right, what bad can happen with that? The receiving end will try to get this object, try to cast it to a non-fitting one, and it will simply fail or something. Well, during the garbage collection process, a method which is called finalize is used. And with this, let's say, vulnerability, Horn was able to control pointers in native code, which gave him arbitrary code execution with system privileges. And a year after, Pelez and Hay, in their paper, One Class to Rule Them All, they did something similar, highlighting a vulnerability which could have gained the attackers, let's say, the ability to execute code with system privileges. This time, they used a non-transient field, which allowed them, again, to control a pointer in native code, giving them, once again, arbitrary code execution with system privileges. Now, when it comes to parcellables, these are also not actually immune to this kind of attacks, as I said. And there is actually a whole class of vulnerabilities which stems out from the mismatch between writing to a parcel and reading from parcel. The first one was discovered by Mikhail Bernarski in 2017, who managed to get what we call launch anywhere. So he was able, simply said, to use the start activity method with system privileges, which allowed him to trigger any kind of component activities, basically. even if those activities were not exported. Again, in 2021, Mikhail managed to use a similar vulnerability, and this time he managed to get arbitrary code execution with system privileges. All right, so I guess the developer community is aware of these kind of issues, and actually they are familiar with parcels, with serializables, and all these kind of classes, due to the fact that some of the most common most common classes in the Android operating system are actually parcelables, like the intent or the bundle. There seems to be, though, a misconception when it comes to custom classes and custom objects. So Android apps are apparently sandboxed, each one treated as a distinct Linux user, which creates the illusion that one application cannot interfere with the class loader of another app or the code of another app, which, as we're going to see, is, as I said, an illusion. So take, for example, this case here. So on your left side, we have a parcelable class, which forms an HTTP request. So we have, it is parcelable. It has the URL which this request should be sent to. It has the, if it is post or get a request, we can define it with this field. And we can define also the data part if it is a post request. Now take a look on the other side. So this is taken from an exported component, which means that it communicates with other apps. So this component checks if the incoming intent contains an extra which is called fragment class. If such a thing exists, then it will try to get another, let's say, extra which is called fragment args. It's a bundle. It will go through the specific bundle and try to check if there is such an instance. If there is such an instance, it will simply send it. It will send the specific post request. So as you understand, if we manage to send such a parcel, such an object to the specific app, we can control the specific request. And the specific case was authenticated, but we will get back to this one after giving you some more context. So how this attack, when this attack, let's say, can be done, when it's achievable. So when it comes to serializable, there are some specific conditions. Of course, it must be the object that we want to send must be serializable. And despite the fact that this seems obvious, remember what I said about Jan Horn's case. So it must be known to the deserializer, which means that, once again, it should belong to the path of the receiving end's class loader. And a thing which stands only for serializables is that the sending, let's say, app, class with the receiving one must have the same version. Think of it as something like a version. So we are talking about a specific UID, which must match between the sender and the receiver. This is not usually a problem because we can set it manually. It's actually a field which we can set. But if it's not set, if it mismatches with the receiving end, then we're going to have the following error. Finally, some other checks that might take place is if we are trying to serialize a transient field, which doesn't make sense, and the field names of the receiving class and so on. Now, when it comes to parcelable, similar things. The class that we want to send must be parcelable. I show you how it looks, at least. And it must be known to the deserializer. And once again, the receiving end must provide the methods which can be used in order to create a parcel out of a receiving one. All right, so now that we know we have some base regarding parcelables, serializables, class loaders, and all this kind of stuff, let's see how we can create an object of a class which belongs to another app. And we'll start with the simplest way to do such a thing. So the most obvious is to replicate, let's say, the fully qualified name of the class, and we can do that very easily in some cases. So we can simply, let's say, create the specific class. We can copy the codes from, let's say, if we decompile the specific, let's say, app or the dex file, we can get the actual code. We can create then a package, add the specific class there, and we can create instances of the specific object. There's nothing to stop us here, right? So this thing works pretty much very well with simple cases, but it can become very tricky when we are facing more complicated cases, like this one here. Imagine we have a parcelable which links to another class, that links to another one, and to add to this chain the fact that in most cases, Android apps are obfuscated. So we're going to have a mess. And this, let's say, way to creating classes is, in many cases, impractical. So it can be used only in very simple cases. Let's keep that. Now, when it comes to the other one, it's a lesser known technique, although it's pretty much straightforward. So the only thing that we have to do is just to get the dex file or the APK file that we want to create, from which we want to create a class. Then use a tool like dex2jar in order to create a jar file out of the specific APK. And finally, import this jar to our project. And then we can simply create, once again, classes. Now, what is the disadvantage in this case? The disadvantage is that the final, let's say, size of our app has to include another app, which, so it makes it quite large. And nowadays, I would say that apps are quite large, despite the fact that Google tries to mitigate that with bundles and all these kind of things, although they are still, I mean, quite large. But the biggest issue in this case is the fact that we might have conflicts between the libraries that we are importing and the libraries that we already have in our project, so we have to exclude some libraries manually, which makes also this process a little bit tricky in some cases. So I would just reject this one too, I mean, in most of the cases. And I'm getting to the best way, according to myself at least, in order to create this kind of objects. So it's dynamic code loading, and when it comes to Android operating system, dynamic code loading can be done with multiple ways, using the memory DexClassLoader, or the DexClassLoader, or the PathClassLoader, with the last two being among the most popular ones when it comes to the Android operating system. Now, the first one is a little bit more flexible, gets a path to a specific file and can load the classes from the specific, let's say, file. The second one is a little bit more strict. So it gets two arguments. The first one is the installation path of a directory. The second one is the parent class loader. It's optional, it can be null. So we can, let's say, omit that. Now, just notice what I said here. So we said the installation path to a directory, right? Can it be any directory? Yeah, so we don't break any kind of law here when it comes to the Android operating system. The code of every app is stored in world-readable directory, so we can give the specific path as an argument here, and we can actually read the specific code. We can get the class loader. So any issues regarding that? I mean, any troubles? The main issue in this specific case is that we can predict the specific path due to the fact that the installation directory of apps include random generated base64 strings. It's out of the scope right now to describe how these are created, but we can keep in mind that we can't simply predict the installation path of an app. Any workarounds? So before actually Android 11, this was trivial to do. So we could use a couple of, let's say, APIs, a couple of methods, and ask the package manager to give us the installation path of a specific app. This changed in Android 11, and we can't do that at least in a straightforward way. So we have to include this entry in our, let's say, manifest file. So imagine that I want to get some info about the com.example.store app. I have to add the specific query entry in the manifest. That's it. And I can get information about the specific app. Another way to do the same thing is using the query all packages permission. Although if you plan to, let's say, post this, publish the specific app to the Play Store, for example, you need to justify the usage of this permission due to the fact that it is regulated, so you can't just use it without any kind of justification. All right, so I guess I said the best for last when it comes to make our life easier. So the create package context is another, I would say, powerful method, which can be, among others, used in order to return a class loader of another app. How we can do that? First of all, gets two arguments, package name, for which we want to retrieve the class loader, and a flag or a set of flags out of the ones which are depicted in this slide. So when we use the specific method, it will call the create resources method, which will wrap up everything, including the application's resources, the class loader, to a context object, and send it back to us. Now, it's worth to mention here that the specific content object is exactly the same with the one which is assigned to every app during its initialization, let's say. All right, and a couple of things regarding these flags that are depicted once again here. So out of specific interest for this briefing are the first two, the context include code and context ignore security, which when they are used in combination, they can allow code execution in the caller's process, in the caller process context. So actually, just to be more clear regarding that, then there is a warning in the Android developers page when it comes to the specific, let's say, method. So when this method is used in a non-secure way, it can lead to arbitrary code execution, and how this can be done. So there is an example here. Imagine that we have the victim app on your left side, and this victim app uses the create package context with these flags that we said before, and then tries to load the class and invoke a specific method of this class. Now imagine that we have another app installed on the same device, which has the only condition in this case is to start with com.victim.module. That's the package name. That it should start with that dot. So now let's assume that this app has implemented the main interface in this way. So it uses the runtime.exec in order to run some code. Now, when the left app, the victim app, executes the specific code, it will simply execute the code which is, let's say, used by the other app in its own, with its own ID, with its own process. So as I said, it's a little bit, needs a little bit careful when we're using the specific method. All right, so what we've seen so far, it is possible to get the class loader of another app, right? And what we can do with that? So we can use reflection, and for those who are not aware with what reflection is, a powerful Java, let's say, feature, which is used in order to inspect objects dynamically, among other things. It belongs to the java.lang.reflect package, and some, let's say, main components of it are the class, field, method, constructor, and so on. Now, in this case, we're going to use the load class method. The load class method gets a name of a class and can return a class object, out of which we can get various types of metadata, including the constructor of a class. And we can use this constructor in a way that, one way to use it actually is this one here. So we can use the constructor in order to create an instance of the specific class, right? So we can get the name, we can give the name of the class, we can provide arguments that we control, we have, it's our own, let's say, data, and we can construct an object. All right. So, yeah, that's highlighting them. So let's see what we have so far before we go to exploitation cases. So an app can access and use the class loader of another app as long as both of them are installed on the same device. This is something which is beyond any doubt due to the fact, like I said before, that Android stores this, the specific code in world-readable directories, so we don't break any kind of law. These allow us to load classes defined in other apps and create instances of those classes, right? With data, of course, that we control. And last but not least, if a class is parcelable or serializable, it can be sent to another app. Now imagine this to end up something like a hot potato. So we are creating an object, we provide our own data, and we're sending it to another app. And the impact, apparently, of this action depends on how the receiving end will handle our own data. All right? It might not have a security impact, it might have a security impact. We're going to see some cases. So how frequent is that? Actually, it is extremely common. And when I say extremely common, I find it almost in, I don't know, 30 to 50% of the apps that I'm reviewing and checking. So it is extremely common. Developers have the bad habit, let's say, to get these kind of objects from external apps, from other apps. So I assume that they don't know, I don't know, that this can happen. Anyway, So let's see some actual showcases, exploitation showcases to put everything in practice. Right. So the first case that we're going to talk about is about an intent redirection. And for those who are not familiar with Android-related vulnerabilities, intent redirection happens when we force another app to send an intent with data that we control and with its own identity. It's actually very important, and if Play Store has a specific, let's say, requirement regarding the specific vulnerability, it should be fixed in a specific time, or else the app can also be removed from the Play Store. So it is important, as you understand. So let's see how this happened in this case. So this code, first of all, is taken from an exported component. Once again, it communicates with another app. So the first thing that this code is doing is checks if the specific intent, the incoming intent, has an extra request. And then it checks if the specific request is of a type request class, this type that you see in this case. And finally, if everything is fine, it will send it to the handle request method that you see on the last line. So let's now check what this request class is doing. So this request class is abstract. It is extended by the iRequest class. So we can create an iRequest object in the specific case. And this one has a private field, which is an intent, right? This one here. We can provide our own intent, I guess, if we manage to create such an object, and by using the specific constructor. And when this intent, let's say, is received by the other app, it will do the following. So it will check if the object that we send is an iRequest instance. If it is such a thing, then we'll simply get the intent and use a start activity in order to send it. So it's a classic case of intent redirection. We can use this one in order to, let's say, trigger any not exported component of this app activities, apparently, or read the content providers and so on. Now, let's move to the next case, which is even more, let's say, easy to get. So this one is about an account hijacking, and this is something which occurs it's something that, let's say, very common when it comes to this type of vulnerabilities. So let's see how this applies. In this case, once again, the specific code is taken from an exported component, which means that the intent can originate from this component. So it will check if it has an extra which is called insider, and it will finally try to cast it in application collection fragment. So if everything goes well, we'll see what will happen. So let's now take a look on this specific, let's say, object. So it has two fields, the about and the collection URL. So we can even create such an object with the method that I showed you in the beginning. I mean, it's pretty much straightforward, just two fields. We can reconstruct the specific class. Now, when this collection URL is received by the other app, it will use it in order to perform an HTTP request, sending the user's token. So we have a session hijacking in the specific case, since it will leak the specific token to a URL that we control. Simply said. Another case regarding a support argument, which, and I name it support argument due to the fact that we're not going to use the specific parcelable in order to exploit this vulnerability, but we're going to use something similar. Anyway, so it was about a few months ago that I read a post about an issue in Jetpack library, which can allow someone to use fragments which don't supposed to communicate with other apps. So what you see here actually is a navigation graph which has this specific fragment. And in order to call this fragment, we have to use some specific arguments, like the URL, and the last one, which is serializable, as we're going to see. Now, take a look here. The last one doesn't supposed to be nullable, which means if we try to trigger the specific fragment, exploiting this Jetpack, let's say, issue, if we try to exploit this thing, if we try to send a specific URL, then we're going to have the following error. This will fail due to the fact that an argument which was required is not there, right? So we have to include a specific argument. That's the point here. And it is a serializable, so I guess we can do it. We can create one. And by the time that we submit the specific serializable, and we send also the URL that you saw as the other argument, then the app will get it and send once again the user bearer token, so we have an account hijacking in the specific case also. All right. Okay, so to conclude this briefing with some takeaways. So first of all, you don't own your own code, and I'm referring to the developers. Of course, you own your own code from the point that you can modify it, you can write it, you can change it, you can do whatever you want, but by the time you're publishing the specific code, nothing stops someone from reading it, and as you see, creating objects with your own, let's say, specific classes or your own constructed classes. So follow security practice in every type of, let's say, class that you are creating in all, from all the points when you want to send a request, when you are obtaining an intent and these kind of things. Another thing that I'm always trying to convey in all of my talks when it comes to vulnerabilities that regard Android apps. So as you see in this case, this requires another app to be installed on the same device. So when I'm discussing with security researchers, even security researchers, or I mean, people that are related to Android, they are saying, okay, what is the likelihood of someone downloading another app from the Play Store which will finally exploit the specific vulnerability? Because as I said, it is mandatory to have another app to do that. So I can assure you that Play Store, any kind of, I mean, app store, they are struggling with malware daily. So this is not something like the user has to download another app and so on. So it's how much we trust the developers that will have already an app uploaded in such marketplaces. So if there is such a thing, 100% has to be fixed, despite the fact that it requires another app. All right. And with that being said, I guess we have enough minutes to get questions if you have any. Thank you very much.